Now that we've seen how a stack is set up in memory and the operations that we can use on a stack, namely the push and pop instructions, let's see how we can keep track of procedure calls using the stack, and also how we can remember the return address where we need to return at the end of our procedure call, and the return value we need to get from that procedure. How do we keep track of those using a stack? Okay, let's take a look at an overview of the procedure call and what happens in that one step at a time. So we're going to start off with two procedures, a caller and a callee. The caller is going to set up some arguments for calling a second procedure, the callee, and then execute a call instruction, which will change the flow of control to the first instruction in the assembly code corresponding to the callee procedure. What's going to be in that assembly code is probably some stuff about creating some local variables that this procedure will need, then some computation in here, then we'll probably get a return value created, and that'll be what this procedure will want to give back to the caller. Then there might be some stuff to clean up the local variables that were created, reclaim the space, and finally a return instruction to tell the CPU that we want to give control back to the caller and go back to the very next instruction after the original call. That next instruction will probably start the process of cleaning up the space that was used to set up the arguments in the first place, and then go find that return value that was created here in the callee. Okay? And that's the process of calling a procedure. Set up the arguments, get the procedure executed, clean up the arguments, and find the return value. Okay. So the callee has to know, though, where does it find those arguments? Where did the caller put them? We have to have some agreement about that. The callee must also know where to find the return address. Where's this address after the call instruction that I have to go back to when I'm done with the code in the callee? All right, the caller must know where to find the return value that the callee generated. Where's it going to find that? And then since the caller and callee are running on the same CPU, of course, they're using the same registers in that CPU, they have to make sure that they don't step on each other. So if the caller is going to use some registers that the callee also wants to use, it better save them away before it gives them to the callee, before it gives control over to the callee. And similarly, the callee might want to save some things as well. Which one is going to do what? Are we going to give all the responsibility to the caller, or all the responsibility to the callee, or some combination of the two? Okay, so we now embellish our diagram a little bit. You'll notice that now we've added, maybe we need to save some registers before we get this call set up. The callee might want to save some other registers. Again, we have to decide how we're going to distribute that work. And if it saves some registers, it needs to make sure to restore them before it returns, so that the caller will find the same contents there that it started things with. And similarly, the caller may want to restore some registers after the callee is done. Okay, so this convention of where to find these things, where to save them, how to coordinate all of this activity is called a procedure call linkage. And we're going to look at the detail for the IA32 Linux way of doing this procedure call linkage. There are many others. Every operating system and programming language has slight variations, but this is what we're going to be using for C on Linux. Okay. Now, the last question at the bottom is asking, of course, if our program didn't follow these conventions, we'd be quite confused about how to do this, and we'd have to think individually about every procedure and what it might have done, or where it might have put things, what it might need to save, and so on, and that's just too much of a burden on the programmer. That's why we like to have a particular convention, and then we can assume it's always done the same way. Okay, so let's take a look at this in a little bit more detail and see how this relates to the use of the stack in memory. Okay, how we're going to use it to support this procedure call and return. So we've seen we execute a procedure call using the call instruction, C-A-L-L, and we give it a label as an argument, namely the address of the callee function. What function are we going what procedure are we going to go and execute next? So what we're going to do is, before we do that, as part of that call instruction, we are going to push the return address onto the stack and save it there. What address will that be? That's going to be the address of the instruction immediately following the call, the one that we have to go to when we're done executing the procedure, and we would execute next after the call. Okay? And then we'll jump to the label, or namely the address of the callee instruction, just as if it were a jump instruction. So as I said, the return address that we've saved on the stack is the address of the instruction immediately after the call. So let's take a look at a little fragment of code here. Here's a call instruction that is going to go to this particular address to execute the next instruction in a different procedure. So the address immediately after it is going to be this address of the very next instruction that happens to be a push instruction. But that's totally coincidental. That could be any instruction. The important thing is that this is the address that we want to return to, so our return address will be that value. What we're going to do is push that value onto the stack so that when we execute the return instruction in the callee procedure, we can go to the stack and pop that value off and then jump to that value, to that address. Okay? So the return instruction is going to be a pop followed by a jump, while the call instruction was a push followed by a jump. And you can see the two are complementary. All right, let's take a look at this procedure call in more detail. Here I have that same little code fragment again, a call instruction followed by the very next instruction after the call. And here I'm showing the current contents of the stack. You'll notice that there's a value at stack, 123. That maybe is an argument to this procedure. And you'll notice that the stack pointer, of course, is always pointing to that top element of the stack. And the instruction pointer, where we are in our program, is pointing to the address of the call instruction. Okay? And that's what we're going to execute right now. So here's our call instruction to execute. It says call the procedure at this address. Okay? So what's going to happen? Well, we'll start off with just that contents of memory. The very first thing that we'll be doing is, since we've just read the call instruction, we'll advance our instruction pointer to point to the next instruction. All right? But we're not done executing the call yet. But our instruction pointer will have advanced, and you notice that now says 553. Okay. The very next thing that happens is that we're going to take that value, that address of the next instruction after the call, and push it onto the stack. So you notice the stack grew a little bit. We now have something at location 104, and the stack pointer was adjusted to point to that location. We subtracted 4 from the stack pointer. That's the push instruction. Okay? The next thing that happens is that we have to, of course, go to this address, and the way we're going to generate that address, you'll notice, is by doing an addition to the current address of our instruction pointer. This is a method called relative addressing. You'll notice that in the instruction we have the constant 063D, of course in little endian notation. Here's that 063D, and we're adding that to the current value of the instruction pointer to generate the address of the actual place in memory where the call tells us to go. Okay. Now, why didn't we just put this address directly in the instruction? There was room there to fit that. We could have made this be 80, or rather 08048B90. But we didn't do that. We used this relative addressing instead. And in fact, both kinds of instructions exist in in the x86 architecture. It doesn't really matter though, because the compiler is doing this for us. And it decided to do it with relative addressing. So the shorter value 063D, and that just gets added to the address. Okay, so this is not something you need to worry about generating. Of course, the compiler takes care of all of that when it generates the assembly code. I'm just explaining how we actually get the address we really care about going to. Okay, so that address then replaces the instruction pointer, because that's the next instruction we're going to go to. Okay, so we are now executing that next instruction in that callee procedure. We're going through that entire set of instructions for that procedure, and finally we'll reach a return instruction. That's at the end of the callee procedure. Okay, when we hit that, the stack will hopefully have returned to the same position. So the stack pointer is pointing to that return address we had saved away, and now what we're going to do is pop that stack and get that value back so that we can go to that location next. So what the return is going to do is it's going to pop this value from the stack and push it into the instruction pointer. Pop it and store it into the instruction pointer. So that's what we see happening here. That value moved there. And of course we have to adjust the stack. That's the other part of the pop instruction. So the stack now changes to 108, pointing back to where it pointed to before we called this procedure in the first place. And our next instruction to execute is going to be at that address, which is, remember, that push instruction following the call. The last thing to talk about in this portion is what do we do with return values from a function. And by convention, values returned by procedures are placed in the EAX register. The choice of EAX is pretty arbitrary. Could have easily been a different register like ECX or EDX, but we've chosen EAX. That's part of that procedure calling convention. The caller has to make sure to save that register before calling a callee that might return a value, because that callee is going to overwrite the contents of that EAX register. So this is part of the register saving convention we'll see later on. So at the end of the procedure, the callee procedure, the return value is placed in EAX, and of course EAX is only 4 bytes, so we could only put certain types there, things like integers, floats, or pointers. Of course, if we want to return anything that's bigger than 4 bytes, probably the best thing to do is to just return a pointer to that object rather than the object itself. Okay, so the thing to remember for now is that upon return, a caller procedure finds the return value of the callee in the EAX register.